want to start with a question that sounds like it belongs in a science fiction novel. What if you've never been outside a black hole? Not metaphorically, not poetically. I mean that right now as you're watching this, you and I and every galaxy we've ever observed may exist on the inside of one. And the most unsettling part, the math actually supports it. This isn't fringe science. It's peer-reviewed, published physics from researchers at serious institutions. And once you understand the argument, you may never look at the night sky the same way again. Let's go back to basics for a moment because the foundation here matters. A black hole is defined by two things. First, a singularity, an infinitely dense point where our equations break down, where the known laws of physics stop working. Second, an event horizon, the boundary of no return. Cross that line and nothing comes back out. Not matter, not light, not information. Inside the event horizon, something strange happens to the geometry of spacetime. The direction we call the future no longer points outward in any direction. It points inward toward the singularity. There is no escape, not because something is blocking you, but because every possible path forward leads deeper in. Now hold that image in your mind and let me describe something else entirely. Our universe began from an infinitely dense singularity, the Big Bang. It has a boundary called the cosmic horizon, beyond which light has never had time to reach us. We are surrounded in every direction by a limit we cannot cross. And within that boundary, the laws of physics are consistent and self-contained, operating the same way everywhere we've ever looked. An infinitely dense origin, a boundary nothing can cross. A self-contained set of laws. If you described a black hole to someone who had never heard of the Big Bang and then described the Big Bang to someone who had never heard of a black hole, you would be describing the same structure. That is not a coincidence. At least, some physicists think it isn't. The idea that our universe exists inside a black hole is most associated with two physicists, Smolin and Nikodem Poplawski. Smolin is a theoretical physicist at the Perimeter Institute in Canada. In the early 1990s, he proposed something called cosmological natural selection. His argument goes like this: when a massive star collapses into a black hole, what if, instead of simply compressing into a singularity, it bounces? What if the extreme density triggers a new expansion, a new Big Bang inside the black hole, creating a baby universe? Smolin took this further. He suggested that baby universes wouldn't be perfect copies of their parents. The physical constants, the strength of gravity, the mass of an electron, the speed of light would be slightly different each time, subtly mutated like offspring inheriting genes with small variations. Over cosmic timescales, universes that produce lots of black holes would produce lots of offspring. Universes whose constants don't allow for stars or heavy elements would have few black holes and few descendants. The result is a kind of natural selection, not for life but for universes. And because the constants that allow for black holes are very similar to the constants that allow for stars, chemistry, and life, we'd expect any universe produced by this process to look a lot like ours. That's Smolin's idea. It's elegant, it's troubling, and it has a feature that most theories of this scale lack. In principle, it makes predictions. Universes that survive in this framework should be near optimal for producing black holes. Our universe appears to be. Then there is Nikodem Poplawski, a physicist at the University of New Haven. Poplawski takes a more mathematical route. He works with a modification of general relativity called Einstein-Cartan theory, which incorporates something called torsion, a property related to the spin of matter. In standard general relativity, a collapsing star produces a singularity. Full stop. But in Poplawski's equations, torsion creates a repulsive force at extreme densities. The collapse doesn't reach a singularity, it bounces. And that bounce, contained within the event horizon, unfolds as a new expanding spacetime, a new universe. Poplawski specifically focuses on rotating black holes, called Kerr black holes, because rotation is the rule, not the exception. Nearly every black hole we've ever observed is spinning. In his model, the rotation gives structure to the interior, allowing a new cosmos to unfold without the traditional singularity ever forming. Let's sit with what this means if it's true. Every black hole in our universe would be the seed of a child universe. Our galaxy alone contains millions of black holes, stellar remnants, intermediate mass objects, the supermassive black hole at our own galactic center, Sagittarius A. Each one a potential universe unto itself. Somewhere inside each of those, if the theory holds, there is a new spacetime expanding right now. Billions of years of history unfolding in an interior we can never see, governed by physical constants that are almost but not quite like ours. And our universe was born from a black hole in a parent universe, which was itself born from a black hole in a grandparent universe. It doesn't bottom out anywhere we can reach. It is universes all the way down and all the way up. We think of black holes as endings. The star exhausts its fuel, gravity wins, and the star is gone. That's how the story gets told. But in this model, that's only half the story. The other half is happening somewhere we can never observe, a new beginning triggered by that same collapse playing out over timescales we can barely imagine. Every few seconds, somewhere in the observable universe, a massive star dies. And if Poplawski and Smolin are onto something, every few seconds a new Big Bang is triggered. Not in some abstract mathematical space, in a real physical interior, sealed off from us by an event horizon, expanding into its own future. There may be civilizations right now inside black holes in our galaxy asking this exact question. I want to be straight with you about something because I think good science communication requires it. This is a hypothesis. Compelling, mathematically serious, peer-reviewed hypothesis, but it is not established fact, and there is a reason for that beyond just waiting for more evidence. The most significant challenge facing both Smolin's and Poplawski's models is that they are extraordinarily difficult to test. If a child universe exists inside a black hole, it is causally disconnected from us by definition. The event horizon that seals it off is the same event horizon that makes it undetectable. We cannot send a probe in and receive a signal back. We cannot compare our constants to those of our parent universe. We cannot, even in principle, confirm the existence of a grandparent cosmos. This puts these theories in a philosophically awkward position, one shared by other serious ideas in physics like the many worlds interpretation of quantum mechanics or certain versions of string theory. They are coherent, they are mathematically consistent, they may even be beautiful, but they sit at the edge of what science can currently confirm. Smolin's cosmological natural selection does make a testable prediction that our universe should be near optimally tuned for black hole production. Many physicists find this promising, others find it too vague to be useful. The debate is ongoing and unresolved. What I'd encourage you to take from this is not certainty either way, but a genuine appreciation for how strange and open the deep questions still are. A century after general relativity, we still don't know what happens at the center of a black hole. We still don't know why the Big Bang produced a universe with these exact constants. We still don't know whether our universe is the only one. These are not gaps waiting to be filled by obvious next steps. They are genuinely hard problems, and some of the smartest people alive are working on them with real humility. Here is what I keep coming back to. We tend to think of black holes as symbols of destruction, the end of a star, the consuming darkness, the place where physics gives up, and maybe that's partly true, but the universe's history is full of things that looked like endings and turned out to be transformations. The death of stars scattered the heavy elements that make up your body. The asteroid impact that ended the dinosaurs made room for the evolutionary path that led to you sitting here watching this. Endings and beginnings have a way of being the same event viewed from different sides. If the black hole cosmogenesis model is right, then death and creation are not opposites in this universe. They are the same process, operating at scales we can barely comprehend. Every stellar collapse is a birth announcement. Every event horizon is the edge of a new history. And we, this small, brief civilization on a pale blue dot, inside a middling galaxy in one possible universe among uncountably many, we are the proof that the process works. That given the right constants, matter becomes chemistry, chemistry becomes biology, biology becomes something that looks up and asks where it came from. We might be the singularity of another reality. We might be someone else's Big Bang. That, I think, is worth sitting with. Next week we're going inside. Specifically, we're looking at the mathematics of what actually happens at the center of a black hole, what Einstein's equations predict where they break down, and what theories like loop quantum gravity suggest might replace the singularity entirely. If you want to go deeper on anything we covered today, the papers by Poplawski and Smolin are linked in the description. They're more readable than you'd expect. Thank you for watching. Stay curious.